Great. Okay. Hello, everyone. Thank you very much for coming. Welcome to this month's UKAN Underwater Acoustics Special Interest Group webinar. This time we have Rasmus from Irwin Carr Consulting, and he'll be talking about practical underwater noise modeling for the offshore industry. Unfortunately, Monika was pulled away last minute and isn't able to join us this time, but hopefully we'll hear her talk at a future webinar. Great. So we've got a great number of people here today. Thank you very much for coming. So yeah, while we just wait for people to get connected, I'll just share with you a couple of upcoming events that we're organizing in the Underwater Acoustics SIG. But yeah, just to start, ordinarily we would have two speakers, speaker one, then speaker two, then a panel discussion. But today we'll just have the one presentation and Q&A afterwards. So yeah, if you have any questions during the talk, just stick them in the Q&A box. And if you'd like to ask a question directly through the power of voice, then just let us know and I'll allow you to unmute. Okay, so the upcoming events that we have on the 4th of March 2022, we have a Connecting SIGs event. So when the UKAN network was conceived, we promised to support ongoing research in acoustics, encouraging new research that's strategically important to the UK. And we identified 4 grand challenges, which fall under artificial intelligence, sustainability, manufacturing and transport, and well-being. And alongside industry, we're helping to support research in those areas, funding pilot studies, and hopefully those pilots will lead to larger scale grant proposals. And so the Connecting SIGs events are aiming to build cross-disciplinary research communities to develop new ideas for proposals under these umbrellas. And the sustainability theme event is what's happening on the 4th of March. So that's a virtual event where there'll be presentations from established researchers and industry people, and also some PhD talks as well, and plenty of time for discussion about what sustainability means for us in acoustics. Also on the 21st of April, we've got an Underwater Acoustics Data Challenges workshop, and that's a hackathon style event where we'll have challenges and data sets provided by industry partners. And then over the course of the event, it's an in-person event at the University of Sheffield. And over the course of the day, we'll be working on these challenges to try and come up with new ways of solving industry problems. Okay, so that's plenty from me. So for the benefit of anyone who didn't join immediately, unfortunately Monika is not able to join us today, but we'll get her on in a few months. And so now, thank you very much to Rasmus for coming. I'll hand over to Rasmus and his presentation on practical underwater noise modeling for the offshore industry. Thanks very much.
Yes. Thank you, and thanks for coming, all 51 participants. I'll just see. I'm going to share my screen here. Ben, on top of yours.
Great. Mine should disappear, I think.
And that should go up. Now, Ben, you're the only one on noise. You can see this?
Yes, that's great.
Lovely. Thanks, everybody, for coming. I don't know if you can see me or not. I'm waving at you. I'm Rasmus, and I've been asked to do a small 20-minute talk. I'm allowed to go a little bit over because the other girl is not attending today. I'm from Denmark, so apologies for any weird pronunciations. Yeah, I did a master's in underwater noise, or specialized in small cetaceans in the University of Southern Denmark. That's Can't remember when I graduated. I don't know, 8 years ago, I think. Anyways, I went traveling a bit and found a job in Northern Ireland here doing underwater noise modeling, which is a bit outside. I'm a biologist by training, so I've had to learn kind of on the go. And we are developing and selling an underwater noise propagation tool called DBC. I'm going to mention it today, but it's not going to be an ad for DBC today. But basically, I've been working in now an industry field for the past 6 years, but still being allowed to kind of do a little bit. It's not academic research in the strict sense, but because it's a field that's very much still moving, and compared to my colleagues that works in terrestrial noise or airborne noise, it's a lot less settled, and the guidance document vary by country, and the regulators don't really know what to make of them often, if there are guidance documents, if there aren't, and it's very much about still digging through academic literature and finding out what's good practice here. So even speaking to my colleagues in the United States, we will say, we usually do this, and they're like, why are you doing that? We'll never see that over here. Or they define impact over there in a different way than we do here. So basically now I'm working in a small an SME in Warm Point, Northern Ireland, little seaside village. And even though we're here, I've been a little bit around the world, but only virtually. So we have jobs from Galway Bay to Taiwan and the Antarctic in the last year, but I haven't gotten to go any of the places. I'm just sitting behind my desk looking at Google Maps. But basically tapping into lots of academic data sets to get the data, or public data sets. Anyway, I'll start. I don't know, Ben, can you answer me? Can you see my mouse on the screen?
Yes, I can.
Brilliant. So I can point a little bit. That's good. That's good. So this is going to be a little talk about the general process I go through for when we ask to do an acoustic impact assessment, because there's things you can do in academia that's very technical, and I like to just call them very academic. And what I mean is that's in contrast to applied, where you can do things very, very accurately. But in the real world, where you have uncertainties, we often just apply a safety factor or conservative factor, and then say, well, we're very unlikely to have a higher impact than this, and we don't really care that we're not accurate. What we care is that we don't underpredict the impact when we do modeling often. So so it's not necessarily about getting the absolute right result. So I'm going to go through what we normally do when we go through an acoustic impact assessment. We find out, well, what's the scope of investigation? There's a project here, and the client might not know the legislation very well, or might not know what actually makes noise. They'll be like, well, our boat is very noisy, or they could be yeah, they often think their boat is very, very noisy, which it can be, but it's often not the deciding factor. So one of the starting steps to figure out in this project, it could be an offshore installation of wind turbines. If the sediment is quite hard and you have to do some trenching that's far enough away from the wind turbine, then from the impact piling that might occur with the installation of the foundations, that trenching of the cables might be a thing that people don't think about. So that could be a significant noise polluter that we also have to go in and model as part of the impact assessment. While something like that's often forgotten as well is that ships, they go, oh yeah, we have these ships out there, that's fine, they're just making vessel noise. But then modern ships have positioning systems that use very, very high frequency and often very, very loud little chirps, or the frequency modulated sweeps, basically, either in their echo sounder, or if they have advanced positioning systems that work against deployed little units on the seabed, then they use those noises as well, and they could be well above 200 dB at frequencies that harbor porpoises would be impacted by. And often they wouldn't think about that. Be like, yeah, we're doing impact piling, that's what we need to assess, but we need to ask what other vessels are in the area or other noise sources. Then a huge part of the work is to generate the actual noise models before you actually do the modeling, and gather data about the environment you're going to do the modeling in. Then you model the activity, and then depending on the local legislation, have a look at what you need to do with the receivers. So these be the animals, basically the environment. And then we have to have a go at figuring out how sure are we, or how uncertain are we at the results. So legislation in underwater noise, it's a lot less regulated than it is for noise in air. Probably because humans have been around in air for a long time, and we have a lot of laws regarding human well-being. So in most of the world, it's quite a complex assessment, where there's some sort of this phrase will be found in legislation. You can't have high risk. You have to show there's a low risk to a local protected population. So even though harbour porpoise might be widespread here in the UK waters, there could be a local population that we're not sure move around too much, or a local population of, especially in Ireland, there's a local population of bottlenose dolphin in the Shannon estuary, and they don't really move much out of there. So even though there's loads of bottlenose dolphins around, well, if you end up assessing that you will impact a few individuals in the Shannon, that's quite a lot of the local population. But there's very rarely you see a very hard and fast guideline that says you can't disperse an animal more than this, or you can't. So there's all these kind of slightly soft formulations in the legislation for underwater noise still. You can't willfully disturb is something that's in the Irish legislation. You can't willfully disturb a protected animal in its place of reproduction. And it's a little bit soft and hard sometimes to pin down. Luckily, I often just deliver stuff to ecologists that have to work this out, but other times we don't, and it's often fine to stick through to Southall 2019, which is kind of in civil terms supersedes the NOAA 2018. I'm not sure if you're aware of it, but it's a framework that uses acoustic weightings. So just like an A weighting or B weighting for humans in air, they use weightings for different species groups underwater. And then after you weigh the noise with these weightings, there's then a limit that dictates, well, if you're below this limit, you're unlikely to cause any lasting hearing damage or hearing loss to the species. And there's another threshold that's slightly lower that says you're unlikely to cause any temporary hearing loss. And then there are other thresholds that aren't based on a lot of evidence, and it becomes more soft after that. There are behavioral thresholds as well, but it becomes very, very hard to figure out at what level can this species no longer communicate between each other. What's the reduction in range? You start getting into all these kind of habitat range reductions, and we generally don't do that. The regulators I've worked with have all accepted some form of this. These frameworks where you have a weighting you apply to the noise, both for it, depending on the impulsive or continuous noise, and then you have a look at if they have temporary or permanent hearing loss from it. There's one country that started very early on having regulations. That's Germany, and that other countries that have adapted this. Basically, for impulsive noise, which is anything that it sounds like a short sharp noise. There are slightly better definitions, but they're not great yet. That's another thing. Impulsive noises, as you go away from the source, become less impulsive just from all the reflections from the seabed and the sea surface, and they kind of get drawn out and become less impulsive in nature. So what's impulsive, what's not? We're generally quite conservative because the thresholds are harsher for impulsive noise. So we generally just apply them. But in Germany, basically, at 750 meters from your activity, you have to be below 160 dB LE, which is exposure level, or 190 dB. They still use peak to peak, I think, if I put this down correct. So that's quite, and there's no weightings or anything. You just go and measure at 750 meters, and if you're below, you're fine. If you're above, you're not fine. So that's quite an easy one. In Denmark, they have like a mixed model where they have they have limits that are species specific, but they weren't weighted. But they've begun to adopt the kind of more the Southall approach as well. But then in Denmark, they go further, and they tell you, well, if you are to have fleeing animals that move around in your modeling, this is the flee speed you have to give it. So it's 1.5 meters in Denmark. You just let them flee at 1.5 meters per second directly away, and that's accepted because it's given by the regulator. I haven't seen that elsewhere. But as far as I know, many countries are moving towards, and it's certainly been the framework that we assess to in in projects abroad and outside Europe, outside Germany, basically. So a step here could be, I'm just going to take an example from a job we did in the Baltic Sea, where the client, we have to fish a little bit with the client, what equipment do you actually have? And it turns out they have all these different bits of equipment on their boat. So they have an echo sounder, so they know where they are, and they have and sonars as well, because they're actually mapping the seabed. And then they have various different sediment profilers that basically ride over the sediment at different depths, and then they use usually now these aren't very low frequency, so they are looking for just the very top layer of the sediment to map that. But they can be quite noisy, and they're quite noisy often in frequencies that are very relevant to marine life. Here it was, I think, grey seal, harbour seal, and harbour porpoise. And then they have these positioning systems and also an altimeter, which basically tells them precisely how far they are above the sediment. They need this for their sonars and stuff to work, I think. I'm more interested in how much noise it makes. So basically, I map all these out on a third octave band frequency, third octave band graph, and figure out, well, how loud are these different ones? Because it's likely that I don't have to model all of them, because every one of these pieces of equipment I need to generate a source model for and stick it in. So anything here that's far enough below the other ones, I can basically just take out. So this sediment profiler here is just a lot less noisy, and is fully within the other noise sources. So it's underneath the graph at any point, so I can just take it out. And then also there's variations in this boat, because it would go along transects, and then it would turn some of the equipment off, and then it would do a long turn. So doing this turn, the client would say, well, we not make as much noise during the turns. It's probably irrelevant for the total impact, but that's something the client would like to see, that when they're actually making less noise, we are applying that. So we are applying that to the model, and that means all their sub-bottom profilers are not running. They're the lower frequency bits here. They're not actually running during the turn. So it'll go up in a transect, and then come back around doing a turn, and then do another transect next to it. It's often how it happens in these kind of seismic explorations. This is also a seismic exploration, but it's just to figure out the sediment. It's prior to putting in a wind farm. So they don't need to know anything about the deep layers, just the top substrate, if it will carry a pile, basically. And for most of these, there are you can make fancier propagation models that will take into account the directivity of the source. But because we're interested in saying to the client, listen, after we've run this, if you're good to go here, we're definitely good to go. You're not going to record levels that are higher than what we modeled. It's very unlikely, or it's for very few, very small time periods it's ever going to be louder. We don't care so much about the directivity. And we are probably partially lucky then that most boats are, and this kind of seismic equipment is loudest broadside, so out to the sides, and not so loud in the direction we're traveling. So it doesn't matter that much directivity, but it's something that if you talk to more academically minded underwater noise modelers, they would be very much, we have to have this directivity, because it does make a small difference. But if you're running that close, then you should probably have more measurements before you start anyway, because the uncertainty in environmental factors are much greater than the uncertainties you're going to get from including a lot of these what I would call smaller nitty-gritty details. For example, you just don't have really good sediment maps, or you don't have really high detail information of what is the water going to do in terms of salinity and temperature exactly where you are. Especially this was in the Baltic, so there's really, really strong temperature differential, because you have water coming down from the inner part of the Baltic that's fresh water, but also really cold, and you've got mixing kind of slightly salty water coming out through the Straits of Denmark. So that's going to have a huge effect compared to other smaller details. Then the biggest part of my job, what takes the most time when we get new jobs, is actually modeling the noise sources. So we have a set of in-house noise models that are based on academic literature. It would be lovely to have a sit down, some large body or something, and say these are the accepted models, and we'll make it available to everyone for a reasonable price. But at the moment, everybody has their own, and the ones who sell it is very expensive. It's a little bit of what we're doing with DBC. We're guilty of it ourselves, I suppose, except DBC is cheap compared to, well, I say that, but yeah. So we have implemented a version of the CMST airgun model. It's, I think it was Curtin University that made it, and there's a paper on that, so everybody can just go in and read it and then run that. I think ours is running in Kotlin, but you could implement it anything you want, and it works quite well. And then we have collected, we have quite a large in-house library of recordings, and then we've calibrated against that. So our models are semi-empirical in the sense that they take the analytical model and then we apply recorded levels. If I know there's a certain type of air gun out there that's being used for what I'm assessing, and I have recordings of that air gun, and I know it's got particular, it's got less attenuation in these bubbles that come after. Sorry, if you're not familiar, this is an air gun firing. It's a very, very sharp pulse, and then depending on the design of it, you have very little small bubbles afterwards. So basically it pumps out a lot of air really quickly and generates a low frequency, very, very high, very high pressure impulse, and it's great at penetrating sediment. But depending on the actual design, the model will spit out the same waveform, because the model only takes in how deep the source is sitting and the size of it and the pressure in it. But different designs means that the air escapes the source at different rates, or there's even some sources that pump out a little bit of air a little bit later to make sure the bubble doesn't collapse and you get less oscillations afterwards. So depending on those, depending on what source is being used, we can modify our source model. So that then has to be presented to the client, and they have to be happy with it. And you can see a selection of different kind of small, I think these were for an Arctic survey, where you have different size air guns. There's a really large air gun having a lower frequency peak, but actually not giving a lot more energy at the higher frequencies. So this would penetrate quite a lot deeper into sediment usually, the low frequencies. And then these being smaller air guns with lower volume tend to have a slightly higher frequency, but they're all, like this is all below 1 kilohertz. So to dolphins and harbor porpoises and seals, the main danger from these would be the quite high peak pressure, not the actual exposure level from them, because the weightings are then applied and they're practically deaf at those frequencies, most of those animals. And deaf, I say, because the weighting is something like -40 or -60 dB maybe at those frequencies, so they don't hear very well. And the assumption is then that they're not going to get hearing injuries as well, unless only from the very high peak pressure if they're close. One of the other piece of equipment we often see are something like pingers and chirpers in echo sounders. These are used quite a lot. Even there's something called a marine vibrator, which is a new kind of seismic source. That's basically a giant big loudspeaker underwater that can do exactly this thing. It can generate a frequency modulated signal. So it starts at one frequency and then slowly ramps up the frequency maybe, and they can do this at let's say 200 dB, but they have a lot lower peak than something like an air gun. And you can tow them. You can either tow them on surface, you can also tow them further down, and it gives you much more control over exactly the frequency content, and it also gives you much more control over the source level than an air gun actually does. So these are being tested at the moment in industry, and they're basically a giant big chirper. And what you could do with them is you taper the pulse off with usually a hand window, and that gives you something like, I think it's 6 dB per octave, so 3 dB per third octave band. So this is much better than if we go back. Something like an air gun tapers off really slow up to high frequencies. While even though this is a chirper for top layer, but if you want to go into a marine vibrator, they work in the same way, and you can really limit the frequency content very rapidly at over like 100 hertz, which means you're only going to impact something like larger whales. So the low frequency group in NOAA South Hall frameworks, the baleen whales basically. Then the hardest thing to model of all is impact piling. There's so many variations on the hammer that's being used, the pile interaction, especially with the sediment. We have a client in the United States, and they have hit something something that's quite soft, a little bit like mud. It's further down the sediment, but then what's happened is it kind of grips, it gets sticky as the pile goes further down. So usually when you hammer a pile into sediment, as the pile travels past the sand or the particles in the sediment, it abrades them and makes them finer, and it slightly decreases the friction. But this increases in friction every time you hit the hammer, so it's almost impossible to predict well something like implant piling. So we have huge uncertainties whenever we pile it, and there's also the effect of whenever you increase the penetration of a pile, the bit of the pile that sticks out into the water, which is if you think about the pile as a resonating body, it's shorter and shorter, so the resonating frequency becomes higher and higher. And so you get different frequencies as you install the pile. And often what we do is make a representative, if you have harbor porpoises in the area, we would pick this scenario where we produce frequencies that are relevant at levels that are relevant to the harbor porpoise, but not necessarily assess all. It could be 500 blows, or it could be 1,000 blows to get the pile into position. You will very often not see that. You will see people go, this is what it looks like all the way down, and we'll pick out a few things, probably the loudest ones. Other things we tend to model are something like vessels, but vessels are nice in the sense that they are, there's a lot of recordings out there of vessels. So it's usually all right, but otherwise we can get there are a few. This is like the model space of simpler models you could run in a spreadsheet, and they give you, depending on the vessel speed and the vessel size and how basically dimensions on the water, but also a shape factor of the hull underwater and cavitation and so on. Depending on the speed that the vessel is designed for, they give you different frequencies. And depending on what type of ship, you might use different models. Some of these are designed for military ships, and some of them are designed for civil ships, and some of them are based on bulk carriers, while other ones are based on ferries. So you have to choose kind of or not ferries, but similar smaller vessels, but they might be quite noisy. But for different reasons, the large vessels might be noisy. So we have a reasonably good grasp on it, and quite a lot of recording. So those models aren't very analytical. They're more, we just have a look at what's out there that's similar to the one you have in your project. And then for environment setup, this is for the modeling. We have to collect as many variables we can on the actual environment we're going to do the modeling in. And this is very relevant later, because depending on the season that you take these environmental data from, the sound propagation is going to be different, which means you're going to have a very, very different impact. So we have to collect, let's say, a whole season's worth of data if it's a site that varies, because otherwise we cannot know if the project gets delayed. So it was meant to be a summer project, now it's become a winter project. Does that make a difference? It probably does, especially if it's a slightly shallower area. So databases like, I don't know if you know EMOTnet, they're a European database, and they have sediment data and bathymetry data for EU and beyond at very, very high resolution, and it's freely available to everyone. It's something that we probably couldn't do our job very well without. And then water temperature, salinity, current, and tide. A lot of this is actually open source. It's just not very well, it's not in one single database, and not necessarily easy to access. And this is where I do a lot of going through academic papers. Somebody did something on the Baltic Sea, and I can extract data from that. Somebody did something on it could be a river in northern England somewhere. Somebody did a project on that, and I'm a PhD project, and I'm taking data out of that, because these things aren't in a central database. But if it wasn't there, I'd need to go over and make the measurements over a year, and it'd be a lot more expensive. Then we need to actually model the activity, and what do I do here? So what we usually do to get around, because of all these complexities I mentioned, we could model 20 different scenarios of saying what happens with the sediment here, what's happened with the sediment, if a sediment is in one way, if it's in another way with the temperatures. So what we do is we generate a few models with maybe the different sound speed profiles, have a look at what does that mean for the propagation loss, and then say, well, we take a best estimate. It could be a median on average of all the different parameters. So we know that warmer water will have less transmission loss than colder water generally, unless it generates a certain type of sound speed profile. So we will take something we estimate it being a likely scenario, and model that, but then also do a high estimate scenario, usually where we just stick to the 90th percentile of the values that we know will decrease transmission loss and therefore increase the estimated impact, because it's going to be higher noise if there's lower transmission loss. So then we take like the 19th percentile if we have enough data to do any sort of statistics on it. Otherwise, if we have like 2 or 3 values, we just take the one that gives the lowest transmission loss, and in that way present the client with 2 different scenarios, but also the regulator later on, so they can see, well, this is probably likely, this is how far it'll go. So you get, this is an impact piling model solely based on recording. So they're recorded levels that are back calculated to a source at 1 meter, to a standard source distance. And there's a reasonably good correlation between the pile width or diameter and then the source level. The exposure level is the red one, and the zero to peak level is the black one. And the reason this is reasonably good is that most of these measurements are from the North Sea. So the measurements that don't fit so well are from outside the North Sea. So the predictive powers of the model aren't as great as you might think. ITAP, I'm not sure if you're familiar with it, but at the German project, they have recordings of thousands upon thousands of impact piling events in the North Sea, and with quite few parameters, you can get really narrow, good confidence bands on your models, just by using the depth at the site, the hammer, and the pile width. And it's because basically all the sediment is almost the same, and a lot of the piles are similar, and they use kind of similar hammer types. So a lot of those things you don't have to account for because they're already the same. But as soon as you go outside that, and you might go a little bit into a river, or you might go to other sediment that's either gravelly or with sticky substrate, you get these outliers quite quickly. And it's just because there hasn't been many recordings made that this model I think is quite neat and nice. But then, so if we're outside those, then we'll have to basically have to we have a model as well in-house that takes the sediment stuff into account, and then we usually ask the client then to have recordings as well in the field, so we can quickly, when you run propagation models, you calculate the propagation loss, and then later on, if you get a recording, you can adjust everything in your model with kind of one click. You don't have to run calculations again. You can just adjust the source a little bit and then get an adjusted view. So we usually ask the client then to get some their permit can be conditional that they have recordings later on. Then we get into the modeling, and we can cover the whole frequency spectrum. I just put in here, usually the models give kind of the same output. So this is a side on a transect view of RAM is the open source version, and Kraken is an open source version. They're kind of different mathematical approaches to modeling, and Bellhop is a ray tracer, but also an open source, and these are just our in-house ones, and basically they agree really well. DBC Ray has been modified a bit, so might handle some of this. Is quite low frequency. It's not, Bellhop's not meant to perform here at these low frequencies, but DBC Ray works reasonably well at these frequencies as well, and the models agree quite well, but they're not. There's a little snout on this blob up here that doesn't agree with the modal solver, and it's not. There are these variations in the modeling. Not going to go too much into detail here, but basically the different models have strengths and weaknesses. The ray tracing, which is basically shooting out a lot of rays from the source and then calculating how they refract through the water and through the sediment, is not very good at dealing with the sediment in general. So you see too little noise energy up here being absorbed by the sediment, while the parabolic equation solver and the modal solver both have a lot of energy being absorbed by the sediment, and thus actually, which is more correct for this quite shallow scenario, where the low frequencies, 16 or maybe 63 hertz, are more absorbed than the sediment. While these two solvers get very, very inefficient at high frequencies, they're theoretically still accurate, but they just become very, very inefficient. And then you tend to use the ray tracer. So I'm going to run a little bit quicker now. I think I'm not running out of time because I have the whole hour. But in receivers, basically, we have, again, in the States, we'd never be asked, rarely be asked to do a receiver or an animal that's moving and see how that reacts. But here in Europe, we quite often will be asked, what happens when this animal starts to move? Does it move away? Can we assume it moves away? So we have different ways of dealing with it. What we usually do is introduce a few. Here's just 5 on this graph, and the black line will be a vessel or something that's moving. It can also be stationary, and you can have these animals react. They basically try and swim away from the noise source and they have different probabilities of response. We can alter that in the model, and they can have different maximum minimum swimming speeds, or they can migrate. Maybe some of them will tend to migrate, and as soon as they're below a certain threshold, they'll start migrating again, and then you get the exposure level, but also the max RMS. So you can model that as well. We usually don't introduce this unless we're close to let's say if you see this, if you're the regulator and you sit and you're close to a limit with receivers that don't move, which is unrealistic, but it's usually an overestimate of the impact, and you then see in the report that they start to introduce moving receivers, it's because they're quite close to the limit usually, because moving receivers that move away will usually have a lower received level than animals that just sit stationary and kind of let the noise come to them. So here's just an example of what a map could look like. So the best estimate, this is inside a river, and they're doing some piling. Best estimate of a single strike for harbor porpoise here would look something like this, where you would have a temporary threshold shift within the yellow zone and permanent hearing damage within the red. While if you have a scenario where you assume the worst, you get something like this. So basically, if a harbor porpoise passes by here while there's piling, you're quite likely to have a temporary impact on their hearing, at least a temporary impact on their hearing. Obviously, this is just for a single strike. There'll be multiple strikes by the time it passes. So we'll have other maps to say what do we imagine the time is going to be for a harbor porpoise to pass here. So that's the end of this. I think I'm not too much over 20 minutes. So I'm just going to escape this. Do you want to steal the screen, Ben?
No, that's fine. If we get, thank you very much, Rasmus. Yeah, keep your slides available, and potentially if we get some questions that mean you want to refer back to them, then that's useful. So yeah, feel free, anyone, to put some questions in the chat or the Q&A, and either I can unmute you and you can speak, or I can. You can ask a question via proxy through me. That's fine too. But yeah, nothing coming in yet. So I was. You mentioned quite early on the flee speed.
Yes.
So the speed that animals can or will retreat at. How does that come into things?
So I wonder if I can start from this slide. Actually, I don't do these very often. So often this is the thing we rely on academic literature as well. Quite often these reports are done with the client, and there are swimming speeds that are reasonably accepted in as long as we don't say suddenly, well, it's likely that this animal is going to swim at 5 meters per second away, because that smells like we're trying to make the animal move away as fast as possible. So for harbor porpoises, it's generally in the industry and with the regulators accepted that they will move away based on papers published that show harbor porpoise avoidance of impact piling. I'm thinking in relation to impact piling here, that they move away to quite large distances. That presents another problem: how far away are you disturbing them? But if we're just looking at animals that are quite close to the source. There are a few papers out there, and it looks like we can get sustained speed of at least 1.5, maybe 2 meters per second for at least an hour. They've been tracked. And that is gonna cost. That there's a metabolic cost associated with that, of course, that dispersal. So you can then assess how far do you think they're going to leave, but that's usually something we leave to the ecologists. But yes, swimming speeds for some of the animals are available in literature.
See, and so when the piling is happening, is it common to monitor what's going on, try and measure whether there are animals in the area who are disappearing off, or do you sort of model
it? Yes, depending on the jurisdiction. Yes, there would be, especially for large scale projects. You'll often have. It's not. I haven't seen very many projects where it's done live, but you might have click detectors and stuff. If it's harbor porpoise water out, that'll try and detect. Where are the porpoises? How many clicks do we detect while piling, before and after and during piling? And that's where a lot of our knowledge comes from. What is the dose? What is the response probability of a harbor porpoise with the received level? That's where a lot of that knowledge comes from. The North Sea, where you have they're probably quite a studied harbor porpoise population, really, but you have these density estimates that are based on click detections. But what you will see otherwise is that you'll have a marine mammal observer either on a vessel close by or on the shore if it's a pier construction or similar, that will try and scan an area. And what we try to do with the modeling is inform, well, what does the range need to be? And that then informs what does the sea conditions need to be. So in the UK, there's generally a 500 meter radius guideline on impulsive noises. That could also be seismic. But there could be settings if you have a very hard seafloor and there's some very large piles where if you can only see to 500 meters, there can easily be animals further away that's going to have acute hearing loss from being too close. And the problem in this is something like a harbor porpoise is almost impossible to spot. Maybe further than 500 meters away, you just need very small waves and you can't reliably spot it. What do you do at night? And then you get into the territory of more noise mitigation. So in the UK, generally, if you have marine mammal observers on and there's no animals within 500 meters or slightly closer, depending on the modeling and the recordings later, you can start your piling. And then if animals come closer while you're piling, that's usually not seen as a breach of the regulations because they voluntarily did it, unless you're like blocking an inlet to the feeding grounds or similar. While in Germany, you'd see a lot more, because you have to be within this limit. They don't care so much about maybe you observing the animals, but you have to be within this limit of 160 dB LE at 750 meters. And if you're above that, you just have to get under it. So if you want a big wind turbine out there with a big pile and a big hammer, then you need to put some sort of either bubble curtain or a casing or something around it to mitigate that noise level, or just have really windy conditions. That helps as well.
Because the
bubbles in the surface, yeah. In a shallow water scenario, you unlikely to see really big piles in shallow water, but yeah, basically really windy conditions, you probably can't do much piling in them. But if it's windy, you get a lot of bubbles in the surface. It means you can't observe the harbor porpoises, you can't see them. But on the other hand, your impact is likely to be lower because the transmission loss is so much higher. Just the natural bubble curtain basically covering the entire area. But it's usually not done because you can't observe the mammals. While in something like we did a project in the States on the West Coast, and they have a lot of sea lions, and sea lions they're in a different hearing group than the OW hearing group, and they're not. I actually have them over here. I don't know if it's a little bit small. They're reasonably good at kind of low frequencies, but they're not as good as something like seals. They're the solid red line, and the dashed red line is the OW hearing group that has the fur seals, basically the ear seals in it, and their thresholds, the limits for temporary threshold shift or temporary loss of hearing is quite high. They also typically very curious and will come right up to your equipment, so you can't have the assumption that it's going to flee, because they just don't. they just come and have a look. So when you model that and talk to the rate, it's a different conversation where you have to model an animal coming right up to what you're doing and maybe swimming away again. So you can't just say you can start and then assume they're not going to come close, because they are.
So we've got a few questions that have come in.
Mm-hmm.
I'll just read them out, I think. So firstly, can specific frequencies be associated with specific behaviors, like mating calls, echolocation clicks, amongst different marine mammal species?
So I'm not well, I am a trained marine biologist, but I haven't done anything in years. So that would usually be a concern where a communication calls you will see for something like the Shannon estuary here in Ireland. It's the Shannon River is the largest river in Ireland, and you have a big estuary, and it has a population of a few hundred, probably bottlenose dolphins living in it, and they travel up and down. It seems they go up close to Limerick, which is kind of at the bottom of the estuary. They seem to go up there to feed quite a bit, and then they head back out, and they might do that a few times a day. Maybe something to do with the tide and stuff. If you introduce, and it's quite muddy and you can't really see in the water, so if you start introducing sounds that don't necessarily impact their hearing but overlap with their communication, which are for these dolphins are mostly maybe whistles, especially mother calf pairs might be whistles. That might be somewhere between 10 and, let's say, 30 kilohertz. Someone might correct me on that, but it's not too far off. If you start introducing a lot of energy in that area, then this is basically a position system here. You could make it impossible for them to communicate, and that could be fatal for a calf in that sense. So the impact of that could be quite high. For clicking, the main impact for clicks. Now, hopperpoppers is a different story, but for most odontocetes, at least, that use echolocation, the clicks are quite loud. But the problem with being, if you introduce background noise, you limit the range at which they're effective, because basically, yeah, it's basically just like shrinking down their habitat a little bit, or the range they can sense things when introducing increasing the background noise. That's something that's generally not being taken into account when you are working in areas that are not seen as being the feeding grounds, or where you're not in a confined area, because it's assumed they can just swim around or swim somewhere else. Yeah, that's the state. There is a lag, I think, in the regulators, where there might be a mandate in the regulation to be quite harsh, but it's not being enforced. So and it's a lot better even in the 6 years I've been working with it. I remember seeing half a page in the report saying it was fine last year, it's probably fine this year, basically. So that's been ramped up quite a lot, which is good. And probably works to the protection of everything. There is another thing to be said for if you have a continuous noise source, such as a big vessel or something, or dredging that's making noise all the time. It's doing a lot of this masking, where basically you could make communication for something like bottlenose dolphins almost impossible. Like their communication range would be tens of meters maybe, instead of several hundred meters. So you're reducing their kind of acoustic habitat quite a bit. If you have impact piling close to that, because it's intermittent, they can communicate in the space between the pile strokes, or between the blows. So you're not actually doing a lot of masking, unless they're close enough to get some sort of hearing impact. But if they're further away than that, they can still communicate, they can still hunt. While if that had been a big ship, then their hunting would have been affected much more, the communication. So it's not perfectly straightforward.
Yeah, I think you touched on the next question I was going to ask, which is what are the biggest struggles when you're doing marine mammal studies? Diego says, are there particular difficulties when working with public bodies?
I don't know. There has mostly that they're not. I don't know if it's not a new area, but it's novel to many of the public bodies. And what I think would be beneficial would be a clearer, not that if you follow the Southall framework and stick to TTS limits, so temporary hearing loss or lower limits, It's quite concrete in the way it's written, but the problem is it's quite technical to follow, and you have a peak threshold. So for the absolute peak pressure, you also have an impulsive threshold for if it's impulsive noise, but for exposure levels. But you also have an exposure limit for continuous noise. So there's these 3 different ones, and then all the weightings, and then you have to deal with the fact if the animal might be moving. So even though there's detailed descriptions of kind of accepted ways to do it, it's still very, very complex. And I think it could benefit for something like the German standard would be much better for a regulator, because you can look, is it above or below this limit? It would mean less work for me probably, but I think it would be better, because it's hard for the regulator to be up to speed on these things, because it is quite technical. I don't know if that answers it, but the main problem is probably education with the regulator, because they don't have a person. Usually they don't have a person that's specialized in figuring out what happens in underwater noise, and they see a report with a lot of numbers and everything, and we try to say this is the worst case scenario, and this is probably a likely scenario. Both of them are, even the high risk is probably okay. The ecologists say it's fine. How can they? The best ecologists aren't necessarily sitting with the regulator. So I'd like simpler guidance, because they would make it easier for the regulator, and therefore make the whole thing more fair and more efficient.
Yeah. Does it make things awkward for you that regulations in the various different places are different as well?
So I always just push. We usually just push for the Southall NOAA, because I'm most familiar with it, because I do it so much, because it's recognized in many places, and that means I have routines set up for it, spreadsheet set up, model set up. Yeah. So if I can run with that, and I can talk to the regulator and say that that's fine, then I can work with that, and that's easier. But definitely, yeah, you have to chat with everyone. And it's not always the legislation is in your native language. We're working on in Mozambique, and I can't remember if that was Portuguese or something, which is not my strong suit. So and then you get, or Taiwan, we got a bad translation of Chinese Taiwanese. Yeah, which was written by someone who clearly wasn't an underwater an acoustician anyway.
I see. I hadn't even considered that would be a problem, but yeah, of course it would be. So I'll just ask a couple more, but I guess we're running out of time. So yeah, just maybe 1 or 2 more. Someone's asking about, Ed Volga is asking if it's currently possible, or whether you do model particle motion in a meaningful way.
So it's a thing we've been looking into, and we advertised for a PhD in it 2 years ago, but nobody bid. So it's something that's being talked a lot about. I never mentioned, actually, there's I put the proper 2014 framework. It's like the same thing for that the Southall 19 is for marine mammals. It does that for fish and turtles. And it also mentions particle motion, and every single conference you're at, they go, well, we should really assess particle motion, and that's fine. And it's mathematically possible to do efficiently in the water phase, because there's quite an easy relationship between particle motion and sound level. So it's not very hard to do in the water column, but I suspect that's not what you're interested in. It would be on the interface, and it's a lot more heavy modeling to do on the interface, and you need a lot more detailed sediment data than we usually have to get the actual particle motion in the sediment and the first kind of few centimeters of the sediment. And then you also get different kind of waves running in the sediment. So if you have pile driving, we model either the sediment as a very viscous fluid, so a very thick fluid, or just as kind of an elastic element, but you still don't get the kind of different surface waves that you actually get, like traveling waves that you get on the sediment from impact piling. You still get it. It's still being modeled mostly just as longitudinal and pressure waves going through the sediment. So if you're into your benthic fish or worms or invertebrates and the like, no, there's not been modeled for them, and part of it is there's no legislative drive for it. So anything that we do, we have a lot sitting in the pipeline that we can we can shove into DBC or shove into the modeling because we can see where it's going, but it's not something we throw a lot of energy at unless it's common in legislation, because the client will never ask for it and they'll go, why do you need to do that? Why do we need to pay you for that? So unless the legislation is there, it's not going to be there it's never going to be applied.
Good.
So yes, you can model it. The sediment is hard.
Yeah, I suppose you're likely to have many different types of species that might have various different limits
yes.
in that sort of environment as well.
What I see happening first is that you go out and make some measurements, and some measurements are available, and you try and do like an empirical fit and just say, well, this is the noise level in the water kind of above the sediment, then it's likely that we're roughly in this region for the sediment vibration, if you will. And but it's not accurate, but it might be enough. But it depends on the thresholds. How many crustaceans can you kill off? How many can't you? It's all based on legislation. So, but it'd be great to see, because there was a paper where there's an Australian paper where they sailed a seismic source up and down a bit and found that, I think it was a mile either side of it, they'd killed like 50% of the zooplankton, and that's not regulated, and it's the base of the food chain. Now they can reproduce really fast, but still, if you're doing this week on week, you could imagine you could take out quite a bit of the food chain locally for that period. But it's something that's hard to say, and it's not regulated.
I see. Yeah, I wouldn't have even considered that something that small could be affected, but yeah.
No, they tend to be, and even if you get close enough to impact, pile driving is very noisy close to the source. Fish fry and stuff will just die if you get close.
I see.
But then there's a lot of them.
On that particularly cheery note,
yeah,
I think we'll bring this to a close, unfortunately, because yeah, we're running out of our hour. But yeah, I'd just like to thank you again, Rasmus, for coming on, and
thanks for having me.
Yeah, there's been a few questions that I haven't managed to get around to, so I wonder if you if you wouldn't mind, if you would like to still ask a question, if you get in contact with me, and I'll forward on your questions to Rasmus, if that's okay. Yeah, so I'll just say thank you very much, everyone, for coming, and yeah, hopefully see you next time. We should be on the fourth Thursday of the month for the next 2 months, and we'll be hearing from the winning entries from the research soundings competition that we ran at the end of last year. Okay, well, thank you very much, everyone, and yeah, see you next time. Thank you again, Rasmus.